Okay, this is not fixed in stone. So there are some steps that can be shifted around a little bit, but generally it goes like this. So the first step is you analyze the beam based on the beam span, based on the loadings, based on the actions. Okay. So according to this information, you analyze it and you determine what the support reactions are. Normally, that's a shear, and you determine what the maximum moments are along the beam. Okay. Once you know the shear and the moment, you select a suitable W. W is the elastic modulus. Later on, later on as I go through the notes, you will know what the term means. Okay. But W here refers to the section modulus. Okay. So you go through the steel table, the table that we went through last week when we do the classification. You go through that table, you select a W that works for you. Okay. And then next, you have to classify the section to see whether it's class 1, 2, 3, or 4. Then only you can determine the bending moment resistance. Once you determine that, then you determine the shear resistance at the point of maximum shear. Then you have to check both together. You cannot check it individually, because if bending and moment, if they exist at the same place, then you have to check both. You have to check your beam for combined shear and moment together. All right. Next, you have to determine the lateral torsional buckling moment resistance. So moment resistance, there are two types. Okay, on a beam, there are two types of moment resistance. One is the section punya moment resistance. Next, there is the lateral torsional buckling resistance, which is the reduced resistance. So you have to check for both. And finally, you check for deflection. Make sure it satisfies the deflection criteria. All right, so that's the process. Okay, now, before we can start, before I can go further, I need to explain to you what lateral torsional buckling is. Okay? So the next few slides, we'll talk about lateral torsional buckling. There. Let me make it bigger. Yeah, make it bigger. All right. Okay. Oops. Okay. So, lateral torsional buckling is, you remember in our first lecture last week, I used that white thing to demonstrate to you what happens when I bend the beam. Yeah. So when I bend the beam, you still remember what happens was the top of the beam, the part that's in compression, it wants to go sideways. Okay. So basically that is lateral torsional buckling. Okay. So I've demonstrated it to you last week using that white thing. And so you know roughly what it does. So in technical terms, basically what it does is when the beam undergoes bending, okay, there is a lateral displacement of the beam. So the entire beam actually goes sideways, but the compression flange goes out more than the tension flange. Okay. And the entire flange, the entire web also rotates. So there is a outward movement, the displacement. There is also a rotation, theta. Okay, both happens together. And it only happens in compression flange. Okay, in parts that experiences compression. Now, you can restrain the beam against LTB. LTB is lateral torsional buckling. I will use short term from now on. But if you see LTB, it means lateral torsional buckling. Okay, so you can restrain the beam against LTB. So there are a few ways. One way is you can build the beam into the slab. So then what happens then is if the compression flange tries to move, the concrete stops from moving, your concrete slab. Yeah. If you build the slab into the beam. If the beam tries to move, the compression flange tries to move, the concrete slab actually stops it from moving. Okay, that's one way. Another way is you can have a shear stud welded onto the beam, onto the top flange. So this shear stud, when the compression flange wants to move, this shear stud will transfer the load into the slab, stops the compression flange from moving as well. Okay, so these are the more common ways for a floor beam to stop LTB. Now, you can also weld other steel members onto it based on the shown on the pictures here. For example, this picture here. Can't make it any bigger. This picture here in the middle. Okay, so if you have another beam connected to your beam, that beam actually stops your beam from buckling as well, from LTB. Okay. So here there are some more examples. You can, some of them are full restraints, some of them are what you call semi-restraints. Okay, they don't fully restrain it. Okay. The most important part is if you can restrain the top flange, that means you can prevent LTB. In some cases, you can restrain the bottom flange, so it stops the entire beam from displacement, but it still doesn't stop the top flange from rotating. Okay. Like this example here. Okay, like this example here, you can see the bottom flange is restrained, but the top compression flange is not restrained. So the sideway displacement is stopped, but the rotation still exists. All right. So ideally, what you want to do is you want to stop the top flange movement. So for example, back to this one. Okay, this is a full LTB restraint. You can see if your beam has another beam connected to it in the side, then this beam cannot move laterally. It cannot move laterally. This beam, the compression flange also cannot rotate because there's something there. There's this plate that stops it from rotating. So in this case, this is what you call a full LTB restraint. Okay, but the most common one are these two, whereby if this is your beam, you build in your slab, you build the compression flange into the slab, concrete slab. So this on top is concrete. Okay, so then if the beam tries to move sideways, it cannot because you have a slab on top stopping it. And if the flange wants to rotate, it also cannot rotate because there's a concrete there stopping it. Okay. In this method, the second method, very similar, but it uses a shear stud connection. Okay, it uses a shear stud connection. Same thing. If the beam wants to move, if the beam wants to rotate, it cannot because you have that fixed. You have that connection stopping it from moving. You have that connection connecting the beam to the concrete slab, stopping it from moving. Okay, so in this case, this is like a symbiosis relationship. Yeah, the beam is carrying the slab, but the slab is helping the beam also in terms of LTB. So they help each other. All right. So there are a lot of other type of restraints. Here you can see, here you have a partial restraint. Okay. And this one that I shown here, this is considered a partial restraint. Okay. It's restraining the beam from movement, displacement, but it's not restraining it from rotation. All right. Okay. So when you classify beam types, so when you design a beam, So why did I talk about LTB? So the reason why I mentioned LTB early is because when you design a beam, you have to decide first, is the beam fully restrained or is the beam only partly restrained? Depending on which type your beam belongs to, you have to take different approach in the beam design. Okay, so your beam is either fully restrained or it's semi, or in some cases fully unrestrained. Okay, but fully unrestrained, you can actually park it under semi unrestrained. Okay, so there are two conditions. It's either fully restrained or it's either semi restrained. Okay, both requires different design approach. Okay, so fully restrained is if, like I say, the web, the compression flange is fully restrained against LTB. Semi restrained means at some point it is restrained, but at some point it's not. Okay, later on you will see there are cases where this happens. Okay, did I include slide for it? Yeah, I didn't. Okay, let me show you what I mean. What semi-restraint means. Okay, I need to sketch. Nah, never mind. I will do it tomorrow. I'll do it tomorrow. Okay, but you just need to know there are these two differences. Okay. Tomorrow in the example, I will explain more to you. All right. Okay. Next, before you design beams, now you have this thing called material partial safety factors. Now, partial safety factors, there are two. There are ones for material. There are also ones for the action. For the action, if you still remember, it's 1.35 G plus 1.5 QK. Okay. This is the permanent action. This is for the variable action. Okay. For the action, you have these partial safety factors. Okay. Now, for materials, you also have partial safety factors. If you remember in concrete design, the concrete strength, the design concrete strength, you have to take the concrete strength divided by some material partial safety factor as well. And I think it's 1.5, if not mistaken. So concrete is higher. Okay. So when we were doing concrete design, you also have to divide your concrete strength by a material partial factor, which is 1.5. Concrete is higher because concrete is mixed on site. So on site, it's dirty, conditions are dirty, and whether you get full strength from the concrete depends on the worker. Yeah, it depends on the worker. So that's why you need to allow for a higher partial safety factor. So you divide it by a bigger number and you end up with a lower strength because you don't know whether you're going to get a full strength or not because everything is done on site. Okay, so for steel, you also have to divide it by material partial safety factor, but it's lower. You can see resistance of cross section, it's 1. So basically, you don't divide it lah. You don't divide it by anything. It's 1. You divide it by 1, you still get the same number. Okay. Now, resistance of member subject to instability, like lateral torsional buckling, you also divide by 1. Okay. It's only in special cases where if you're calculating the resistance of cross sections in tension due to fracture, then you divide it by 1.1. Okay. So generally it's 1. Okay. It's only in special cases you divide it by 1.1. Okay. So why do we use 1, which is basically nothing? Yeah. So we use 1 because steel are produced in factories. So when you produce something in factory, you can ensure there's good quality control. Yeah, there's quality control. So if the strength is 275, you will get 275. So that's why you don't have to divide it to get a lower strength. Okay. 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 Next, we are going to go into the design of fully restrained beams today. Today we will cover back to this. Okay. So for today, for this week, for this entire week, we will cover fully restrained. Okay. Okay. So this week we will cover only fully restrained beams. Very simple. Okay. Fully restrained beam, very simple. Next week, we will cover the semi-restrained part. Okay. Semi-restrained part is more complicated. Okay. So semi-restrained next week. Okay. So semi-restrained, we cover it next week. This week, we focus on fully restrained beams only. Okay. So let's talk about fully restrained beams. Okay. Fully restrained beams. So obviously you need to know how to calculate the moment resistance. You need to know how to calculate the shear resistance. So this is what we are going to go through today. Okay. So fully restrained beams, the moment resistance formulas are all here. Right. Okay. You memorize the formula. Then it's settled for you. All right. So fully restrained beams, the moment of resistance depends on the formula you use depends on whether the beam is class 1, class 2, class 3, or class 4. That's why you have to do your section classification. That's why I taught you how to do section classification last week. Okay? So that you know whether your beam is in class 1, whether it's class 2, whether it's class 3, whether it's class 4, because the formulas are different for the different classes. Okay? So we go through one by one. So if your beam is class 1 beam, now to be honest, most beams that you will encounter is class 1 or class 2. Okay? So to be perfectly honest, most of them are class 1 or class 2. So you need to remember by heart this formula. Okay? The first formula is very important. Most beams are 1 and 2. Most beams are 1 and 2. So make sure you memorize that formula. Okay? So if it's class 1 and 2, then the moment of resistance for your beam is WPL times Fy divided by gamma M naught. Okay, now, if you look at the previous page, gamma M naught is 1. Yeah, yeah, yeah. Resistance of cross section, gamma M naught is 1. Okay. So gamma M naught we know is 1. Simple. So now you just need to know what is WPL, what is Fy. Now Fy is your beam strength. Okay, there's a table I showed you last week. If we use beam, if we use grade 275, then Fy is 275. Simple as that. But don't forget, it's only 275 if your steel thickness is less than 40 mm. If the steel thickness is more than 40, it becomes, I don't know, 235 or something like that. Okay, so it's still governed by the thickness, the steel thickness. Okay, next, so that's Fy, the steel strength. Okay, the yield strength of your steel section, of your steel material. All right. Next, what is WPL? Now, WPL is the, if you look at the bottom, it tells you WPL is the plastic section modulus. Okay, it's a plastic section modulus. It's basically the formula. You may have studied this before in mechanics of solids. It's the formula S. It's the formula. It's also the formula S in mechanics of solid. Okay. In your section table, there is this WPL. So you just choose the WPL that you need in the section table, which is, I'll show you. Okay, I never share with you the table. Still anything ba? This table. Okay. You still remember this table? Oh, no, you can't see it. Wait, I have to change screen. So I change screen now. So what is WPL? Okay, you can see my Excel. Can you see my Excel?
No,
Boleh ke tidak?
Tidak,
Nampak putih saja nih dokter.
Putih aja. Tak nampak Excel table kah? Yang section
Tiada.
table kan? Oh, tidak.
Tiada.
Oh, okay. Okay, saya tutup. Saya buka balik. Wait, still. How about now? Sekarang nampak? Dapat?
masih lagi tidak nampak.
Masih putih kah?
Ya,
Okay, never mind. Saya screenshot. Maybe it's if I share screen. Share screen. Okay, sekarang nampak?
Sesuaikan sih.
Nampak dokter.
Boleh?
Boleh.
Okay, alright, okay. So, masih ingat table ini kan? Last week, when we did the section section classification. Okay. So, this table, when we do the section classification, we obviously use the first few columns lah. We use the H, we use the B, we use the flange, the web thickness, okay? But if you keep scrolling, to the right, so I'm scrolling to the right now, scroll to the right, scroll to the right, scroll to the right, scroll to the right, scroll to the right. Sini. You can see, ada tu plastic modulus, and then ada elastic modulus. Yeah. So these are the values that you take for your section classification. No, the moment resistance calculation. Okay. This is what you take for your classification, for your moment resistance calculation. So, boleh saya contoh nggak? Ya, boleh. Okay, alright. Plastic modulus, boleh nampak saya contoh kan?
boleh.
Okay, plastic modulus, this is your WPL lah. Ini WPL dia. Tapi it depends whether you do design about the whether the bending is about y-axis or z-axis. Okay, so just to recap, kalau ini beam kamu, ini y-axis, meaning bending this way. Or if this is your beam, z-axis is the vertical one, meaning bending about z. Okay, so normally the bending is about y-axis lah. Normally bending is about y-axis. So use the one in the y-axis, these figures normally. Okay, so plastic modulus. This is the table you refer to. WPL, WPL. PL, you can see that PL plastic. Yeah, PL there stands for plastic. Okay. So this is the table you refer to. You just need to decide whether it's axis or z-axis. So now, okay. Now, if your section, so this is for class 1 and class 2. Class 1, class 2, use WPL. Class 3, later on, when we go back to my notes, you will see class 3, you use WEL. EL means elastic. Okay, so if you section in class 3, then you use elastic modulus direct from this other column. Okay, so all the figures are given to you. All right. So let's go back to my presentation. There, sini. Hey. Sekarang saya tak nampak pula. Hey. Okay. Okay. You can see now I've gone back to my PowerPoint. I've gone back to my PowerPoint. Kalau tak nampak, bagi tahu. All right. Okay. So you can see. Alamak. How come okay, so all right, so if it's class 1, class 2, you use WPL. If it's class 3, you use the WEL. It says WEL mean. Just ignore the mean lah. It's not important. Okay, it's WEL. Okay, you just use WEL. Okay, so class 1, class 2, it's WPL times the steel yield strength Fy divided by gamma m naught, which is 1. Okay. If it's class 3, then you use the elastic section modulus multiplied by again the yield strength divided by gamma m naught, which is again still 1. Okay. So yang ini dengan ini penting. Class 1, class 2, class 3 penting. Most of the time it's one of these classes. Now, if your beam somehow ends up as a class 4 section, then what you have to do is you have to calculate. This one you have to calculate on your own. The W that you use is not from the table, Sudah. You cannot use the W from the table because what you have to do is you have to multiply it by W effective, the effective section modulus. Yang ini kena calculate sendiri. Okay, so you have to use the W effective times the steel yield strength divided by gamma m naught, which again still 1. Okay, so you can see the only difference between class 1, class 2, class 3, and class 4 is the W. W saja yang berbeza, yang semua lain sama. Yeah, only W is different. Everything else is the same. Okay, now fortunately for you, class 4 we seldom encounter. Okay, class 4 we seldom encounter. So you don't have to remember this formula, class 4. Yeah, you don't have to remember lah. Maybe when you start working, you will encounter it. Okay, but for lectures, don't worry, you're not gonna encounter it. So you have to remember Formula One and Formula Two. Okay, class one, class two, and class three. Okay, but easy lah, easy to remember. Class one and class two, plastic. Class three, you use elastic. Yeah, simple like that. Okay, so these are the formulas for moment resistance of fully restrained beams. Okay, now what happens after you calculate this? Okay, so I calculate the MCRD. I calculate the MCRD. What happens after that? Okay, what happens after that? So after you calculated the MCRD, then you have to do this check. This is a check that you do. Okay. Okay. So this is a check that you do. So MCRD you calculate from the formula tadi. Okay. So MCRD is the resistance from the table on the from the formula on the left hand side. Okay. You have to do this check, and then MED is just your moment from analysis. So if your beam is simply supported and it has a UDL, then your moment in the middle of the beam is what? WL squared over 8. So that is your MED. It's your moment from the beam. Okay. So to determine whether your beam okay or not, you have to take the moment from your analysis divided by the resistance from the left hand side tadi. Okay, there. MCRD are here. So you calculate MCRD, you compare it against the beam punya moment. If it's less than 1, then your beam okay. If it's more than 1, then your beam fails. You have to choose a bigger section. Simple as that. Okay. Now, this formula, obviously this formula is for single axis bending. Okay, you're only checking MED. So if your bending is about y-axis, then you check lah, the whole thing. You check about y-axis. You calculate the MED for y-axis. You calculate the MCRD for y-axis. Okay. Now, in some cases, your beam may be subjected to biaxial bending, meaning you have bending about y-axis. You will also have bending about z-axis, y and z-axis together. Yeah, y plus z. So in this case, you have to calculate the y-axis. You have to do the exercise for y-axis. You have to repeat the exercise for z-axis, and then the two together, added up together, has to be less than 1. Okay. So meaning you do this process for y. Yeah. Meaning this formula in green, you calculate it one time for y-axis, and then you calculate it another time for z-axis, and then you add both together and make sure it's less than 1 also. Okay. So that's for bending. Okay. Now, what happens if you have shear? Okay, shear resistance is here, the formula. Okay, the main formula is this. Yeah. Okay? The main formula is this shear resistance. Okay, so I'm going to point out the simple ones. Simple one is this Fy. You also have Fy, like your moment. So you use the same Fy lah. Whatever Fy you use for the moment resistance calculation, you use it here. Gamma n naught is again also 1. Square root 3 is square root 3. So the only thing that's new here is actually AV. This is the only new thing here. The rest are the same as the earlier formula. Yeah. The only thing that's new is the AV there. Okay. What's AV? AV, there are several meanings lah. Okay. But in this context, it's the shear area. Okay. In this context, it's the shear area. AV is the shear area. Okay. So what is the shear area? Now, if the shear area depends on what shape steel beam you are using. If you are using a I or H section, I is basically UB, yeah? H is basically UC. Okay, if you're using UB or UC, I or H, okay, that's a formula you follow. Okay, the formula is A minus 2 BTF plus TW plus 2R times TF. Now, most of these formulas you know already. Okay, most of these formulas you know already. I go through one by one with you. Now, to be honest, all these numbers they are in the section table as well. I'll show you later. A is the cross section area and this is in the Excel table. B is the width. Also in the Excel table. You used this before. You used this last week for the section classification. It's in the Excel table. TF is the flange thickness. Also in the Excel table. TW is the web thickness. Also in the classification, also in the Excel table. R is the root radius. Also in the Excel table. The only thing that's not there is the N. This N value and HW and TW. TW is the web thickness. HW is the web height. Okay, it's the web height. So the web height is the total beam height minus the flange thickness minus the root radius. Okay, now this N thing, we don't know. It's the only thing that we don't know, but there's a note there. It says, N may conservatively be taken as 1 as well. So very simple. Everything that you don't know, you just take as 1. Okay, so N here, you take as 1. So in that case, the AV, to calculate AV, everything you know, everything you need for AV calculation from Excel, from the Excel section table, everything is there. Okay, you just need to follow the formula. All right. Okay, now, so obviously, this is for I and H, okay? I section and H section, UB or UC, okay? Now, if it's a channel section, then you use the second formula, B. Channel is like that, this section, okay? If it's a T section, then you use C, T section. If it's a welded I, or H, then you use D. But normally I or H is rolled. Normally it's rolled. If it's welded, so these two are welded. Okay, welded. All right. The rest we don't have to worry. Circular hollow is this one, but don't have, yeah. Now, these formulas, whether I give it to you in test and exam, I need to think. It's in, all this is in Eurocode 3. It's in Eurocode 3, okay? Whether I ask you to memorize it or whether I give it to you in test exam, I need to think about it. Yeah, I'm not sure yet. Okay, so you follow these formulas, you can calculate VPLRD, the shear resistance, VPLRD. Okay, that's the shear resistance. Next, what you do is you do the same as for moment resistance. There, you have to check that your VPLRD or VCRD, you have to check it against the shear from your analysis juga, VED. VED is your shear force diagram, the shear from your shear force diagram. Shear force diagram. Okay, so if it's UDL, then your shear force diagram is like that. Then you have some value here, you have some value there. So it's this value, 100. That's your VED. Just like what you did for what? For IC design. Okay, same thing for IC design. Okay, you just take the end value, you check. All right. Okay, that is for shear. Now, last. What if you have moment and shear together? Now, normally, before I go through too much about this, I need to clarify for you. Okay, now, in your beam, in normal beam, let's say UDL. Okay, in normal beam, let's say we are looking at UDL beam, UDL loaded beam. Okay, the shear force diagram looks like this. This is the midspan. Midspan. Okay, the shear force diagram looks like this. So, where is the shear force the highest? Someone tell me, based on this diagram, where is the shear force highest? In the middle? In the middle, or is it 2/3, or is it at the end of the beam? Where?
At the end of the beam.
Yeah, end of the beam highest. Okay, it's highest at the end of the beam. Now, next we look at bending moment diagram. Your bending moment diagram parabolic shape for a UDL. Where is the maximum?
Middle of the beam.
Yeah, middle of the beam. Okay. So that's the situation we have. Shear, for shear force, it's highest at the ends of the beam. Bending moment is highest in the middle of the beam. So actually, my point is, they don't act together. Maximum shear doesn't occur at the same place as maximum bending moment. Okay, that's my point. Maximum shear does not occur normally, not all the time. My point is, the place of maximum shear normally is not at the same place as the place of maximum moment. Normally, okay? Normally, they are not at the same place. Okay? Remember this, normally not at the same place. Why do I want to point this out? It's because sometimes you have this situation where you have moment and shear together, and so therefore you have to check it together as well. Okay? You have to check it together. Okay. Now, when do you have to check it? The condition is here. If your design shear from the bending moment diagram, the VED from the bending moment diagram, no, not bending moment diagram, shear force diagram. So when your VED from the shear force diagram is less than 50% the shear capacity, then the shear force on bending resistance may be neglected. However, so VED is from SFD, from the shear force diagram. VPL, this is the resistance. Both of these you learn how to calculate earlier from the earlier slide. Okay? So if the shear force is less than 0.5 the shear resistance, or in other words, 50% of the shear resistance, if it's less than 50% of the shear resistance, you can ignore this issue. Neglect. Yeah, neglect. Just ignore lah. Neglect means ignore. You can ignore this issue. However, if your shear from the shear force diagram is more than 50% or 0.5, the shear resistance, then you have to take into account. You have to account for it. Okay? So you have to account for it. So you have to do all this calculation. So if it's more, then you have to take into account. The way you take into account is you have to do this calculation and you have to do all this calculation here on the right. Okay, you have to do all this calculation. But normally, like I say, you can ignore. Why? This is why I show you the shear force diagram earlier. This is what I show you the diagram earlier. I cannot make it bigger. Never mind. Okay. Shear force diagram like that. Bending moment diagram like that. So what it means is you have to check the beam 2 times. You check the beam once at midspan. Now at midspan, the moment is high, but the shear is 0. Yeah. So if your shear is 0, definitely it's less than VPLRD, less than the shear capacity, or less than 50%, less than 50%. Yeah, it's definitely less than 0.5 VPLRD. So you don't have to worry about the combined shear and moment. You don't have to worry about combined shear and moment, because if it's 0, it's definitely less than half VPLRD. Okay, so you do one check in the middle, and then you do another check at the end. You do another check at the end. Now, at the end, or your VED may be quite high. I don't know how much, but it's definitely the maximum there lah. The VED there is maximum. Okay. It could be more than 0.5. It could be more than 0.5, but there the moment is 0. Then the moment is 0. So again, moment 0. So you don't have to worry about. You also don't have to worry about the combined moment and shear. Okay. So normally in the beam you have to check 2 times. One where the moment is maximum, another time where the shear is maximum. Okay. You have to check once where you have maximum moment. You have to check one more time where you have max shear at the end. Okay. So you have to check it 2 times lah, normally for a steel beam. Okay. So my point is, this check, moment plus shear resistance check, combine moment and shear. Normally, you don't have to check. Okay, so normally this thing, combined moment and shear, normally no need to check. Okay, so normally you don't worry about it. But if you do need to check, then the formula is given to you. Okay, basically what it's about is, the way it works is, I just explained to you quickly. Basically what it's about is, I need to remove annotation. Okay, alamak, I think I stopped sharing screen pula. Okay. Okay, now if you do need to do this check, basically what it's about is, all right, there. Can you see my screen? Yeah? Can, right? Okay, all right. Okay, so normally what it's about is, you have to do a check where you calculate raw. You calculate raw first. Raw is 2 times your maximum shear force divided by VPRD, which is your shear capacity, minus 1, and then the whole thing squared. That gives you raw. After that, what you do with the raw is, you go to the next formula, you calculate MVYRD. This MVYRD is the reduced moment capacity due to shear action. Okay, so basically the way you account it is, if you have shear and moment combined, you have to reduce your shear, you have to reduce your moment resistance. Basically, this is what the formula does lah. It helps you to calculate the reduced moment resistance, and you use this to check your moment for the beam. Okay, but like I say, this situation normally doesn't occur lah. Okay, you can actually adjust your design. Even if it does occur, you can adjust your design so that it so that you avoid this problem. Okay, there are ways to avoid it. Okay, right. Okay, so that concludes the theory part, okay, of the beam, moment, and shear design. Tomorrow we will do the calculations. Okay, tutorial. So tomorrow I'll go through several calculations with you. Once for I may do 1 or 2 for the moment resistance. I may do 1 or 2 calculations for the shear resistance. Okay, so make sure tomorrow you are you are there for the class. All right. Now before that, I will do attendance. Slot. Okay, how do I get back to? Okay, do your attendance now.